Good morning, class. Here's College Algebra Chapter 3, Functions, 3.7, Inverse Functions. We've covered the entire Chapter 3 from functions all the way to absolute value functions, and now 3.7, Inverse Functions. The objectives are verify inverse functions, determine the domain and range of an inverse function, and restrict the domain of a function to make it one-to-one. Find or evaluate the inverse of a function. Use the graph of a one-to-one function to graph its inverse on the same axis. Composition of functions. First, reminding you of the average rate of change, delta y over delta x, or f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. Then there are different ways of representing them. This is the algebra function: addition, subtraction, product, and quotient. If A represents the domain for f and B represents the domain for the g function, the domain of all of these functions, algebra functions, is A intersection B because both f of x and g of x have to be defined. The last one, f of x over g of x, has this extra restriction that g of x cannot be 0. So the domain of f over g is the same thing, A intersection B, g of x can't be 0 because we can't divide by 0. As far as composition of function is concerned, x is a domain of the g is the domain of f, resulting in f o g, and we say f o g of x is f of g of x. G o f of x is g of f of x. And as far as the domain is concerned, g of x must be defined. So any x not in the domain of g must be excluded. F of g of x must be defined as well. So any x for which g of x is not in the domain of f must be excluded. In short, you look at the domain of g of x, and anything that makes f of g of x undefined is also included. Absolute value equations and inequalities. The absolute value of f of x is defined as f of x if f of x is greater or equal to 0, and minus f of x is less than 0. Absolute value of x equals a results in x being plus minus a as long as a is positive. Absolute value of x is less than a, x is sandwiched between minus a and a as long as a is positive. And absolute value of x larger than a, x is less than minus a, or x is larger than a if a is positive. The graph looks like a V shape. This is the vertex located at 0, 0. And the domain is all real numbers. It covers the entire x-axis. The range on the positive side of the y-axis, including 0, so from 0 to infinity. If we take c to be a positive number, and y is f of x, then y equals f of x plus c shifts up by c units, f of x minus c shifts down by c units, f of x minus c shifts to the right by c units, f of x plus c shifts left by c units. Now, if we are looking at y equals f of x, and we take c to be a number larger than 1, then c times f of x, it stretches it along the vertical axis by a factor of c, so c times that. And 1 over c f of x, it shrinks it by the same factor, so divides by c. If you have a negative in front of f of x, it flips it over with respect to the x-axis. If you have a negative in front of x, it flips it over with respect to the y-axis. In other words, reflection with respect to the x-axis is minus f of x, with respect to the y-axis is f of minus x. (3.7) Inverse functions, one-to-one functions. A function is one-to-one if each element in the range corresponds to exactly one element in the domain. In short, in the case of a function, the x coordinates cannot repeat. In the case of a one-to-one function, the y coordinates cannot repeat either. So here's the example. A has the following pairs: 1, 2, 3, 5, 4, 6, minus 2, 1. B has the coordinates, the pairs 1, 2, 3, 5, 4, 6, minus 2, 5. Both A and B represent functions since each x coordinate corresponds to exactly one y coordinate. So if you look at the x coordinates for A, 1, 3, 4, minus 2, they're all different. For B, 1, 3, 4, minus 2, they're all different. Therefore, both represent a function. Set A is also a one-to-one function since each y coordinate also corresponds to exactly one x coordinate. So if you look at the y coordinates of A, 2, 5, 6, 1, they're all different. That's the meaning of it. On the other hand, set B is not a one-to-one function since the y coordinate 5 corresponds to two x coordinates 3 and minus 2. So if you look at the y coordinates, this is 2, this is 5, this is 6. So far, so good. But now 5, that means the y coordinate 5 is being repeated, and therefore this fails to be a one-to-one function. A function f is one-to-one if for any two numbers a and b in its domain, f of a equals f of b results in a being b. And when a is not equal to b, f of a is not equal to f of b. So if we have the same y coordinates, we must have the same x coordinates. If the x coordinates are not the same, the y coordinates cannot be the same. So we use the vertical line test for a function. Now we are going to use a horizontal line test for a one-to-one function. If a horizontal line can be drawn so that it intersects the graph of a function at more than one point, the graph is not a one-to-one function. So this is a function. Yes. Not a one-to-one function. This is a one-to-one function. So this passes a vertical line test. It fails the horizontal line test, HLT. But every function of this sort can be cut into pieces such that each piece is a one-to-one. So as you can see, if we cut this into two pieces, the one to the right or the one to the left, each one is a one-to-one function. So the restriction on the domain can make it one-to-one. Inverse functions, if f of x is the one-to-one function with ordered pairs of the form x comma y, the inverse function, this is read f inverse, this is not f to the power of -1, f inverse of x is a one-to-one function with ordered pairs of the form y, x. In short, when you interchange x and y, you get to inverse function. Given the function f of x equals 1, 4, 2, 0, 3, 7, -2, 1, -1, -5, find the inverse function. So we want to find the inverse function. All we have to do is to rewrite the pairs but interchange x and y. For example, 1, 4 changes to 4, 1. 2, 0 becomes 0, 2, and the rest of them in the same manner. So every pair, x and y, are reversed, resulting in an inverse function. If we were to graph and plot each point for f of x, and then do the same thing each point for f inverse. So we plot all these pairs, we plot all these pairs. Okay. So the blue ones represent ordered pairs for f of x, where the red ones represent the ordered pair in inverse function, points for the two functions are symmetric with respect to the line y equals x. So we can see this from the graph that they are symmetric with respect to the line y equals x. What it means is that if you pick any point from one of them and you drop it perpendicular to the y equals x, and if you continue the same distance, this distance and distance is the same, you get a pair which belongs to its inverse. So each case, the distance here and the distance here is the same. This distance and this distance is the same. That's the concept of symmetry. Find inverse functions. How do we do that? Only one-to-one functions have inverse functions. The domain of f of x is the range of f inverse x. The range of f of x is the domain of f inverse x. The graph of f of x and f inverse are symmetric about the line y equals x when graphed on the same set of axes. So these are some properties we should know. To find the inverse function of a one-to-one function, replace f of x with y. We do that because it makes it easier to work with. Interchange, and that's the key, interchange the two variables x and y. And right at this step, we do have the inverse. However, we normally solve the equation for y and replace the y with f inverse of x, the inverse function notation. Again, this -1 in f to the power of -1 is not an exponent. This is read f inverse. So f inverse of x. That is extremely important to know and pay attention to, everybody. So we don't want to, mix them up. Find the inverse function of f of x equals 4x plus 2 and graph both f of x and f inverse. Let's see how we do that. Number one, we change this to y because it makes it easier to work with. That's the first step. Change this to y. The second step, to interchange x and y. By the way, we can graph this. Okay, we can graph this. As you can see, we have 0, 2, and then, for example, 1, 6. But what about the x-intercept? If you set this equal to 0, everybody. For x equals -2, x equals -1/2. So look at that. Okay, so we should have no problem with that. So if you plot 0, 2, -1/2, 0, this is the line. So just graphing the first function. Now, to find the inverse, we are going to interchange x and y. Y changes to x, x changes to y. And to solve for y, we are going to move the 2 becomes -2, and we're going to divide both sides by 4. And we call the y f inverse of x. So we found from f of x, we found f inverse. We've graphed f of x. We want to graph f inverse, and all you have to do, come up with the pairs. Now, even if you don't want to work them out, 0, 2 becomes 2, 0. I hope you notice that this is y, right? Or you can write here, if you let x be 2, y becomes 0. So this will go to 2, 0. This will go to 6, 1, and this will go to 0, negative 1 half. Okay? I hope you can see that. And again, you can work it out. So this is 2, 0. 0, negative 1 half. Connect them. And you can see symmetric with respect to the line y equals x. This is the line y equals x. So we could write it in this fashion. So this is y equals f of x, y equals, f of x equals 4x plus 2, or y equals f of x. This is y, or f inverse of x equals x minus 2 over 4. And here's the line y equals x, which shows clearly the two lines are inverse functions because they're symmetric with respect to the given line. Graph f of x equals 5x minus 2 and f inverse of x equals x plus 2 over 5 on the same set of axes, and compare. Well, this one, clearly the y-intercept is 0, negative 2. And if I set this one equal to 0, so 0, negative 2 is obvious. And if I set y, or f of x, equal to 0, I hope you see that x is 2/5. So those are the pairs. So we can graph y equals 5x minus 2, or f of x equals 5x minus 2, looking like this. So zero minus 2, 2/5, 0. Now, to graph this, I hope you recognize quickly the pairs are, so 0 minus 2 becomes minus 2, 0, 2/5, 0 becomes 0, 2/5. And you can try it if you just plug it. So you can find those pairs, minus 2, 0, 1, 2, so somewhere here, 0, 2/5, so somewhere here, and you connect them, and that gives you f inverse of x, which is x plus 2 over 5. Here's the line y equals x. The graph of f inverse of x can be drawn by reflecting the graph of f across the line y equals x. So it can be done in that manner. Inverse functions. For any one-to-one function, f of x and its inverse, f inverse of x. F of f inverse of x equals x. F inverse of x equals x. In this case, x in the domain of f inverse. in this case, x in the domain of f. You look at this function, this means f of f inverse, that's one. So, given that f of x is 4x plus 2, f inverse of x is x minus 2 over 4, show the above is true. So, if two functions are inverse, then we should be able to show this property. So starting with f of f inverse of x, we are going to go with 4 instead of x, x minus 2 over 4, and then plus 2. These two cancel each other. You get x minus 2 plus 2, which is equal to x. So it shows that, and that takes care of the business. Let's go with f inverse or f of x. Let's go with this one. So this x will be replaced by 4x plus 2. As you can see, positive 2 and negative 2 cancel each other. We get 4x over 4, which is equal to x. Verify that f and g are inverse functions. So one of this will be good enough. I want you to know that. So you calculate f of g, you get to x, that's good enough. But it's really not a bad idea to do both of them as practice. So f of g of x means f of g of x. And so that means in this function, we're going to replace the x with the g, which is x plus 3 over 4. So we want f of x plus 3 over 4, which means 4 times that. And now these two cancel each other. Clearly, we get x plus 3 minus 3, which is x. And that's a proof, and we are done. I want you to know that. But I like to look at g of f of x as well. Just for practice, so g of f of x means g of 4x minus 3. Therefore, when you go with this function, you replace this x with 4x minus 3, everybody. So what happens? These two cancel each other. 4x divided by 4 is x. Since f of g of x equals x and g of f of x equals x, f and g are inverses. That proves that the two functions are inverse of each other. Find f inverse of x for the function f of x equals 7x minus 4. And as I mentioned, we start with writing y instead of f of x. We are going to interchange x and y. Right here, everybody, we do have the inverse. However, we solve for y, which means we move the minus 4 and we make it plus 4, and then we divide by 7. And we give it the name F inverse. We are done with finding F inverse. However, it's always a good practice to prove we are right, which means we are going to look at either F of F inverse or F inverse of F. One of them is good enough now. So if we look at F of F inverse, it means replace the x here with x plus 4 over 7. So 7 times x is replaced by x plus 4 over 7. We get x plus 4 minus 4, which is x. Since f of f inverse of x equals x and f inverse of O f of x equals x, they are inverses. Now, the second part, class, this part, I'm leaving it for you to verify. I can't emphasize this enough. Okay, you really should try it. So again, one more time. We did just this one. This one is not done. I'm leaving it for you as a practice. Sketch the inverse of the function whose graph is shown. So we have this graph. We can draw the line y equals x and reflect the graph on the line. So we can reflect it with respect to that. So this is the line. So what does it mean? In short, it means pick up a few pairs on the graph given, and then find the pairs corresponding to those for F inverse. And go with the easy ones. For example, this one seems to have coordinates -2, -4. So -2, -4 is a pair on the graph of the function f of x or the red function. So if that is the case, then -4, -2 must be on f inverse. To show you the concept, this means, everybody, f of -2 equals -4 by definition. So that means f inverse of -4 equals -2. If you want to go with the proper way of writing and with all the details, and what it means is that -4, -2 is a point on f inverse. In short, this belongs to f of x. This, if you interchange x and y, belongs to f inverse. I'm showing you with more details here. You don't have to write that, but understand the meaning of it. So this means this. Let's look at another easy point. Okay, so this, by the way, -4, -2. So we are going to locate -4, -2 for the graph of the inverse function. Let's pick another easy one for the red one first. This point seems to have the coordinates 0, 4. So 0, 4 belongs to f of x, meaning f of 0 must be 4, and therefore 4, 0 belongs to f inverse. I'm going to write f inverse of 4 equals 0, and that means 4, 0 belongs to f inverse. So more importantly, we found this point. Immediately, we know if we interchange those 4, 0 must belong to its inverse. So now locate 4, 0, locate 4, 0. So this is corresponding to that. Let's pick another easy point. -1, +3. So in short, if we ignore all the writing, -1, 3 belongs to the red function. 3, -1 belongs to its inverse. So this means f of -1 is 3. So f inverse of 3 is -1. 3, -1 belongs to f inverse. That's the concept that I hope everybody's fine with that. This pair. Now, if this is enough, so be it. If this is not, you can pick more points. By the way, it's important to know, you see this point where the graph crosses the line y equals x. This point, because you're looking for a symmetry, this belongs to the inverse as well. So this is another point that they have. If the two functions ever intersect, they must intersect with the line y equals x. So that belongs to both of them. So it seems to be going this way. So the graph going this way. So you may pick another point here, easy point here, and corresponding here. Easy. See, this is actually, this might be an easy point. Okay, so 1 and 5, 5 and 1. Okay, and then you'll see the corresponding graph for f inverse everybody. Again, I can't emphasize this enough. If you pick those few points and that doesn't do the job for you, you can pick always more points. We know this, we've already mentioned that for every function that is one-to-one, f of f inverse and f inverse of must be the same, it's equal to x. We want to we are verifying that these are inverse function where g of x is x cubed, g inverse is cube root of x. To prove that, we look at their composite function. So if I look at their composite function, g of g inverse, now f of f inverse, so g of g inverse. So instead of x, we're going to put cube root of x. Clearly, when you raise this to the third power, you get x. And that's a proof and you're done. But this is easy enough to do the g inverse g of x. So now if you replace this x with x cubed, put the g inverse of g of x, clearly this is x. And again, we did both ways. One of them, again, I can't emphasize this enough. One is enough, but I wanted to show you both. And now these two functions, both of them are linear functions. F of x is 2x plus 3. F inverse of x is half of x minus 3. By the way, this one was a cube function. It's a cube root function. They undo each other in essence. So if we look at f o f inverse, if we look at this one, That means replace this x with this expression, half of x minus 3. When you do that, clearly, two and 1/2 cancel each other. We get x minus 3 plus 3, which is x. So that proves it. On the other hand, if we want to look at f inverse of, we're going to replace this x with 2x plus 3. And so these two cancel each other. We get half times 2x, which is equal to x. And that's a proof, and it's done.